The diagram above shows an open-topped water tank in the shape of a cuboid, which is made of sheet metal. The base of the tank is a rectangle x meters by y meters. The height of the tank is x meters. The capacity of the tank is 100 meters cubed. Part A. Show that the area A meters squared of the sheet metal used to make the tank is given by A equals 300 over x plus 2x squared. So we're talking about the area of metal needed to make this tank. So let's go through each of the sides. So the base here, the rectangle on the base of this water tank will be x times y, or xy. The side over here will be x times x, or x squared. And there'll be another one of those over there as well. So we'll have 2x squared. Then we've got the front rectangle here, which will be x times y. And there'll be another one of those at the back here. So we've got another 2xy. Excuse me. And the tank was open top, so we don't need to worry about the top. No metal is required for the top there. So we've got the base, the two sides, and the front and the back. Now we can simplify that by collecting these like terms together. So we'll rewrite that as A equals 3xy plus 2x squared. Now that looks a little bit like this, but not quite. I've got a y here, which I shouldn't really have. So let's see what we can do about that y. Because there is some information in the question that I've not used yet. We were told that the capacity of the tank, now another word for capacity is volume. We were told the volume of the tank was 100 meters. So let's see if we can use that information. The volume is 100. Now I know the volume can be found by doing the area of the cross section, which I'm going to write down as being x squared, multiplied by the length. So that the volume of this tank is x squared y. And I'm making that equal to 100 because we were told the capacity was 100. I can now divide both sides by x squared, and I found that y could be replaced with 100 over x squared. If I do that, I find that the area is equal to 3x times 100 over x squared plus 2x squared, which gives 300x over x squared plus 2x squared. And then we notice that these x's cancel out. And I've got the expression that we needed to get here. So that's part A done. Part B says to use calculus to find the value of x for which A is stationary. So that's telling me that the gradient, or dA by dx in this case, is equal to 0. So I want to take my a function and differentiate it. So I'm first going to rewrite that 300 over x as being 300x to the power minus 1. Just so I can differentiate it easily. The 2x squared, that's going to differentiate easily, so we'll leave that as it is. Right, let's differentiate. So the 300x to the power minus 1, we're going to multiply by the power. So 300 times minus 1 is minus 300. And then we're going to take 1 away from the power. So the minus 1, take away 1, is minus 2. The 2x squared will differentiate just to be 4x. And I'm trying to find when does this equal 0 for it to be a stationary point. This is the equation I'm trying to solve to find the value of x for which a is stationary. Now, in order to solve this equation, I don't particularly like this x to the power minus 2 there. So I'm actually going to rewrite this as minus 300 over x squared. And by doing that, that makes it a little bit clearer what my method is going to be, because now I can see that I'm going to multiply both sides of this equation by x squared. By doing that, it's going to cancel this x squared here and leave me with just a minus 300. The 4x times the x squared will be 4x cubed, and the 0 times x squared will still be 0. We can now add 300 to both sides, and then divide by 4. And then if we cube roots the 75, we find that the value of x that makes a stationary is 4.21723 decimal places. So that is the value of x which makes a stationary. So that's my answer for part B. Part C says prove that this value of x gives a minimum value of a. So I need to show that this is a minimum. Now I know at a minimum that the second derivative is greater than 0. So let me take my my first derivative. Remember, this is my first derivative. And I'm going to differentiate this for the second time. So we're going to multiply by the minus 2. The minus 300 times minus 2 will be positive 600. And then we'll take 1 away from the power to get minus 3. When we differentiate the 4x, we'll just get 4. So this is my second derivative. And I need to show that when x is 4.217, this is positive. So if I now do 600 times 4.217 to the power minus 3 plus 4, if I work that out, if I type that into my calculator, I do find that it's a positive number, and I can then say, therefore, a minimum. And that's part C of the question done. Finally, part D. Calculate the minimum area of sheet metal needed to make the tank. So I've worked out the value of x that makes it a minimum. But actually, what is the minimum? How much metal will I actually need to use? Well, I can take that value of x and substitute it into my area equation here. So the area is equal to 300 over 4.217 plus 2 times 4.217 squared. So if I do that, we find that the minimum area of metal needed is 106.7 metres squared. And that's my answer for part D.